Millions of commercial tires are discarded every year simply because their outermost layer has worn away. But beneath a bald surface, the core structural casing is often perfectly intact. Today, these heavy-duty transport tires are entering a second life. The retreading process begins with a rigorous sorting phase, filtering out casings that have suffered deep sidewall damage or structural fatigue. The quality of a used casing depends heavily on the roads it traveled. Tires sourced from well-paved routes maintain their internal geometry, making them ideal candidates for reconstruction. Before any new rubber can be applied, every casing must pass an exhaustive visual and physical check to confirm it can handle the intense stresses of highway transport. Moisture is the enemy of vulcanization. The casings undergo a thorough drying process, driving out any trapped water that could turn to steam and cause catastrophic layer separation later on. Once fully dry, technicians inspect the rubber for micropunctures and hidden structural weaknesses. They employ shearography, a laser diagnostic technique, to detect internal anomalies invisible to the naked eye. Only a casing with absolute structural integrity is cleared for the restoration line. It must be solid enough to endure tens of thousands of miles under load. With the casing verified, the remaining old tread is mechanically ground away. The buff stage reveals the tire's foundational steel belts, exposing minor cuts and gouges sustained during its first life. These imperfections cannot simply be covered over. They must be completely filled to prevent future tread separation. A technician uses a specialized thermal extruder, essentially a high-temperature industrial glue gun, to inject molten rubber directly into the damaged zones. At these temperatures, the fresh rubber flows into the smallest crevices and bonds at a molecular level with the existing casing. The hot filler pushes out trapped air, creating a solid, uniform surface over the exposed steel cords. This meticulous repair work restores the original structural profile, creating a pristine canvas for the new tread. Any exposed wire requires immediate sealing to prevent rust, which would inevitably destroy the casing from the inside out. The repaired sections will cure and harden, matching the density of the surrounding tire wall. With the foundation prepped, the tire is mounted onto a rotating assembly drum to receive its new contact patch. A continuous roll of pre-cured rubber tread, molded with a deep, aggressive chevron pattern, is fed onto the line. This is cold-processed retreading, where the tread strip is already fully vulcanized and hardened before it meets the tire. To bond this thick tread to the buffed casing, an intermediary layer called cushion gum is required. The cushion gum is unvulcanized, highly tacky rubber that acts as the essential adhesive bridge. As the tire rotates, mechanical rollers apply immense, uniform pressure across the width of the new tread strip. This pressure forces out any microscopic air pockets between the layers, ensuring flush contact across the entire circumference. If even a tiny air bubble is trapped beneath the tread, it will expand violently when heated, compromising the bond. The rollers press the heavy chevron strip seamlessly into the adhesive base, marrying the fresh rubber to the seasoned casing. Skilled operators monitor the alignment constantly, making micro-adjustments as the heavy material feeds into the drum. The edges are carefully trimmed and pressed down to create a smooth transition between the new cap and the old sidewall. Every seam must be perfectly flush to prevent drag and resist tearing under heavy acceleration. The cushion gum provides only a temporary physical grip. To achieve a permanent chemical bond, the entire assembly must undergo vulcanization. The fresh tread is meticulously centered and the edges are shaved down using pneumatic tools, ensuring the final profile matches the original factory specifications. A perfectly feathered edge reduces rolling resistance and improves fuel efficiency for the transport vehicles that will rely on these wheels. Once the new cap is fully seated and inspected, the tire moves toward the curing station. To prepare for the high-pressure chamber, the entire tire is encased in a flexible rubber envelope. This vacuum bag seals the assembly completely, protecting the unvulcanized cushion gum from direct exposure to steam and heat while maintaining steady compression. The vacuum extracts all remaining atmospheric air from between the rubber layers, locking the casing, the adhesive cushion, and the heavy outer tread into a single cohesive unit. This intense preparation guarantees that when the heat is finally applied, the layers will fuse flawlessly. The precision required here is absolute. The alignment dictates how the tire will track on the highway. A heavily built transport tire like this carries tons of cargo, and the integrity of this seam is what prevents a dangerous blowout at speed. The enveloped tires are now rolled across the floor, heavy and secure, ready for the intense heat that will finalize their rebirth. A mechanical hoist lifts the enveloped tire, positioning it over an internal curing bladder. This inner tube is heavily reinforced and equipped with brass valve stems designed to hold extreme internal pressure during the heating cycle. Technicians connect vacuum lines to the outer envelope, drawing the rubber skin tight against the deep grooves of the new chevron tread. The assembly is then loaded into a massive industrial autoclave. Inside this thick-walled curing chamber, the tires are subjected to precisely controlled heat and immense pressure for several hours. The internal bladder inflates to push outward, while the external pressure chamber pushes inward, compressing the tire from both sides. Simultaneously, The elevated temperature activates the unvulcanized cushion gum, initiating a chemical cross-linking process. The sulfur molecules bridge the gap between the casing and the tread, fusing them into a solid block of continuous rubber. When the heavy steel doors finally open, the temporary adhesive has transformed into a permanent structural bond. The result is a fully functional transport tire, rebuilt to perform exactly like new, keeping thousands of pounds of industrial waste out of landfills. The finished treads emerge with pristine, aggressive lug patterns, fully cured and ready for the road. Not every tire can be saved. Casings with severe sidewall blowouts or deeply rusted steel belts are rejected from the retreading line, but their material value is far from exhausted. In a massive outdoor processing yard, an excavator equipped with a specialized grapple claw tackles the end-of-life tires. The heavy machinery feeds piles of discarded rubber into an industrial shredder. These twin-shaft shredders rely on sheer mechanical torque, utilizing massive rotating steel blades to bite into the resilient rubber and high-tensile steel cords. The machine tears the rigid tires into jagged, fist-sized fragments in seconds. This aggressive size reduction is crucial for handling and transport. The resulting shredded rubber is highly combustible and boasts a caloric value comparable to high-grade coal. Instead of sitting stagnant in sprawling landfills for centuries, this processed material is shipped out as a powerful alternative fuel source for energy-intensive industries such as cement manufacturing. The continuous flow of the conveyor belt transforms a chaotic mountain of scrap into a uniform, valuable commodity. It is a harsh, deafening process, but an essential one in closing the loop on industrial waste. The raw material is systematically broken down, preparing it to generate the intense heat required for heavy manufacturing elsewhere. Every shred of rubber represents captured energy, waiting to be released. The powerful hydraulic grapple moves relentlessly, grabbing half a dozen heavy casings at a time and dropping them into the hopper. The shredded pieces are stockpiled into vast black mountains, a stark contrast to the meticulous rebuilding happening inside the factory walls. This facility ensures that even the most severely damaged rubber serves a final, critical purpose in the global supply chain. Tires are not the only heavy material being recycled on a massive scale. Deep inside the adjacent metallurgical plant, overhead cranes command a cavernous industrial space. A massive magnetic hoist gathers tons of raw scrap metal, discarded machinery, structural beams, and vehicle frames, and drops it into a heavy-duty loading bucket. The crane operators act as choreographers of chaos, blending different grades of scrap to achieve the correct chemical composition for the upcoming melt. The charging bucket, suspended by heavy braided steel cables, is carefully maneuvered directly over the open maw of an electric arc furnace. At the push of a button, the bottom panels of the bucket swing open, releasing a torrential cascade of jagged steel into the refractory-lined crucible. Loading the furnace requires precise timing and balance, ensuring the scrap is evenly distributed, so the electrical current can arc efficiently across the jagged peaks of metal. The heavy roof of the furnace is then swung back into position, sealing the chamber. This is the first step in the violent rebirth of steel, gathering discarded fragments to be forged into a monolithic structural force. The raw scrap represents the forgotten remnants of past construction, now waiting to be purified. The magnetic crane operates continuously, sweeping the yard to fuel the insatiable appetite of the smelter. Once the heavy lid is lowered into place, the environment shifts from mechanical sorting to raw, high-voltage chemistry. The sheer scale of the bucket and the massive furnace shell highlight the extreme engineering required to tame and recycle heavy metals. The lid locks down, preparing to unleash an electrical storm inside the crucible. With the furnace sealed, 3 massive graphite electrodes are lowered through the roof, hovering just above the mountain of scrap. When the immense electrical current is unleashed, it arcs violently between the electrodes and the jagged metal. The extreme voltage acts as a sustained lightning strike, generating temperatures exceeding 1600 degrees Celsius. The solid steel does not merely melt, it collapses rapidly under the deafening explosive power of the electrical arc. Massive ventilation systems struggle to pull away the dense plumes of smoke and vaporized contaminants. Oxygen is injected directly into the bottom of the molten bath, reacting aggressively with impurities and driving up the temperature even further. As the scrap liquefies, the heavy, pure steel sinks to the bottom, while the lighter slag and oxidized impurities float to the surface. Finally, the furnace is tilted and the tap hole is opened. A brilliant, blinding stream of pure, liquid steel pours out into a heavy, refractory-lined ladle waiting below. The glowing liquid flows with the viscosity of water, entirely transformed from the chaotic pile of rusted scrap just moments before. The intense, radiant heat illuminates the factory floor, a testament to the immense energy transfer taking place. The ladle itself is engineered with specialized heat-resistant ceramics to contain the violent temperatures without melting its own steel shell. This clean, molten extraction marks the transition from destruction to creation. Even after the initial melt, the liquid steel is not yet ready for casting. Workers clad in specialized, high-temperature protective gear approach the glowing ladle to skim away the remaining slag. These impurities, resembling a thick, dark crust on top of the blinding liquid, must be extracted to ensure the final product has the correct tensile strength. The transfer process naturally cools the molten metal, threatening to solidify it before it reaches the casting molds. To prevent this, the ladle is moved to a secondary refining station where smaller electrodes are introduced. This ladle furnace aggressively reheats the bath, driving the temperature back to optimal casting levels while allowing technicians to fine-tune the exact chemical alloy. The intense glow of the 1600-degree steel casts harsh shadows across the heat-reflective suits of the operators. Every adjustment here dictates the structural integrity of the steel that will soon support buildings and bridges. Once the metallurgical chemistry is perfectly balanced and the temperature is stabilized, the refined steel is transported to the continuous casting deck. The purified molten steel is poured from the ladle into a holding reservoir called a tundish, which ensures a steady, uninterrupted flow into the molds below. This is continuous casting. The liquid metal streams down into water-cooled copper molds, which rapidly chill the outer skin of the steel. As it descends through the cooling chamber, the steel begins to solidify from the outside in, forming a thick, glowing square strand known as a billet. The billets are pulled vertically, bending into a horizontal path as they cool just enough to hold their shape, though they remain intensely hot and malleable. Automated torches slice the continuous glowing strand into standardized lengths. These massive red-hot steel ingots are the foundational blocks of the rolling mill. Some billets are shunted aside to cool completely, destined to be sold as raw material to other manufacturing plants. The rest continue directly down the line, retaining their immense thermal energy to feed the adjacent hot rolling process. The metal has taken on its first uniform shape, ready to be stretched and manipulated. While still radiating intense heat, the hot billets are fed directly into the rolling mill. The steel is driven through a series of increasingly narrow, heavy-duty mechanical rollers. With each pass, the sheer compressive force crushes the square billet, forcing the metal to elongate and thin out. Water sprays instantly vaporize upon contact with the glowing surface, managing the temperature of the friction-heavy rollers while blowing away oxidized scale. The red-hot steel behaves like stiff clay, stretching rapidly as it is compressed. What entered as a thick, short block is progressively squeezed into a long, slender rod. The final sets of rollers imprint the characteristic ridges along the surface, transforming the smooth rod into functional reinforcing bar. The steel is moving faster and stretching further with every second, maintaining its malleable, glowing state throughout the violent shaping process. The freshly rolled rebar shoots out of the mill at high speed, completely transformed but still dangerously hot. The long, flexible rods slide onto a massive stepped cooling bed. Here, mechanical walking beams slowly rotate and advance the steel, allowing the rods to cool evenly in the ambient air. If the steel were allowed to cool unevenly or rest in a pile, it would warp and bend, ruining the straight profile required for construction. As the deep orange glow fades to a dull industrial gray, the steel regains its immense rigidity and tensile strength. The organized grid of the cooling bed keeps the rods perfectly parallel as they migrate toward the sizing station. Once the metal drops to a safe handling temperature, the long continuous strands are fed into a heavy hydraulic shear. The thick blade snaps through the bundled steel simultaneously, cutting the rods down to standardized, uniform lengths for the commercial market. The chaos of molten liquid and high-speed stretching has finally settled into precision manufacturing. The cool, rigid bars are now structurally sound, perfectly straight, and ready for final packaging. The cut rebar is conveyed into a mechanized funneling system, where curved green metal guides force the loose rods into a tight, dense cylinder. A continuous chain drive pushes the heavy steel forward, feeding it directly into an automated bundling station. To transport tons of loose steel safely, the rods must be locked tightly together. Heavy hydraulic clamps descend, crushing the rods into perfect parallel alignment. Once the bundle is compressed, an automated wire-tying machine rapidly circles the steel. A mechanical arm feeds a thick-gauge wire around the bundle, pulling it taut and twisting it off with absolute precision. This automated binding is far stronger and faster than manual labor, ensuring the heavy rods will not shift or spill during transit. As the machine secures the final loops, an integrated printer generates and applies a high durability shipping label, detailing the exact dimensions, weight, and metallurgical grade of the steel inside. The process is a seamless display of industrial automation, converting loose material into a standardized commercial product. Finally, a massive yellow overhead crane equipped with heavy-duty electromagnetic pads descends onto the line. The powerful electromagnets lock onto the steel, effortlessly lifting the heavy bundle away for staging and shipping. The cycle of recycling is complete. The scattered, rusted scrap metal has been entirely redefined into essential structural reinforcement, ready to form the backbone of new concrete buildings and infrastructure. But the facility's ingenuity extends beyond heavy metallurgy. The immense waste heat generated by the electric arc furnace and rolling mill isn't simply vented into the atmosphere. Instead, it is captured and redirected to power a massive, high-tech greenhouse built directly adjacent to the factory. In this pristine, climate-controlled environment, the heavy industrial runoff sustains rows of vibrant tomato and cucumber plants. The stark contrast is striking, the chaotic destruction of scrap metal directly fueling delicate agricultural growth. In the end, heavy industry, thermal engineering, and agricultural growth operate as one integrated system. a facility that produces, reclaims, and sustains itself. Some environments find balance in the most unexpected ways.